Okay, welcome everyone to this deep dive.
Great to be here.
Today, we are jumping head first into something truly wild. Einstein's theory of relativity.
The universe's operating manual, almost.
Exactly. Forget, dusty textbooks. We're digging into Einstein's cosmic rulebook, Unveiling Relativity. That's our source today.
And the goal is to make these, let's be honest, mind-bending ideas feel, well, simple, fun, even.
Yeah, absolutely. Especially if you hear physics and think, uh-oh, we want to make it super approachable.
Totally. It's all about perspective, really.
Okay, so perspective. Imagine this. You're on a spaceship, right? Going incredibly fast, nearly light speed.
Zooming along.
And your friend is back on Earth, waving. You both have perfect clocks.
Okay.
Einstein says your clock, on the fast ship, starts ticking slower than your friend's clock.
Yeah, slower. Time itself is different for you.
How is that even possible? It sounds like science fiction.
Oh, that's relativity for you. Maybe we should start with the first piece, special relativity.
Good idea. That came first, right?
Yeah.
1905.
That's the one. And it basically boils down to just two core ideas, two rules.
Okay, lay them on me. Two simple rules for, rewriting reality.
Yeah, kind of. Rule one, the laws of physics. They're the same everywhere, for everyone. Doesn't matter if you're standing still or on that speeding spaceship.
Right. Gravity works the same. Electricity works the same. Got it. Universal rules. What's number two?
Number two. This is the kicker. The speed of light. That incredibly fast 300,000 kilometers per second.
Whoosh. Yeah.
It's always measured as the same speed. Always. No matter how fast you're moving when you measure it.
Wait, hold on. So if I measure light speed standing still, I get that huge number.
Yep.
But if I'm running towards the light source super fast, I still measure it going at that exact same speed. Shouldn't it seem faster?
Logically, yes.
Yeah.
But experimentally, no. It's constant. And because that speed must stay the same for everyone.
Something else has to give.
Exactly. Our usual understanding of space and time has to bend to keep light speed constant, which leads to some really weird but real effects.
Like time slowing down, that's time dilation, isn't it?
Precisely. Time literally passes slower for you the faster you move relative to someone else. The source calls it a secret time machine.
So on my spaceship trip, I come back, and my friend is way older than me.
Could be. If you went fast enough for long enough, yes. Your friend aged faster.
Wow. Okay. Mind officially starting to bend? What else?
There's also length contraction. That spaceship you're on, to your friend back on Earth as you zoom by.
Yeah.
It would look shorter, squished, sort of, but only in the direction you're moving.
Like a cosmic shrink ray hit it?
Yeah, kind of like that. It appears compressed.
Okay, so special relativity is about speed messing with time and space. But what about gravity? That came later.
Yep. About 10 years later, 1915, Einstein unveiled general relativity. And this one tackled gravity.
Right, the force keeping us all grounded. What was his big idea there? Did he change gravity?
He totally redefined it. Forget gravity being some invisible force pulling things together. Einstein said massive objects like planets, stars, actually warp or curve the fabric of space and time itself.
Space-time, like they're connected.
Woven together. The source uses a great analogy.
Yeah.
Imagine space-time as a giant stretchy trampoline.
A trampoline. Okay, I can picture that.
Now put something heavy on it like the sun. What happens?
It makes a big dent, a curve in the trampoline fabric.
Exactly. That dent, that curvature, is what we experience as gravity. Planets orbiting the sun aren't being pulled by a rope. They're just rolling along the curve, following the dent the sun makes in space-time.
Whoa. So orbits are just following the curves. That's elegant.
Isn't it? It's geometry on a cosmic scale.
Does this warping affect time, too, like speed did?
It absolutely does. Time also slows down. The stronger the gravity is, the deeper the dent in space-time.
So time, you're a really heavy thing, like a black hole.
Runs much, much slower compared to time far away from it. Another way, time isn't fixed.
Okay, so speed slows time, mass slows time, and mass curves space-time, which is gravity. It all sounds connected.
It is. Mass and energy are equivalent, remember EMC squared. And it's mass energy that tells space-time how to curve. And space-time tells mass how to move. It's all linked.
So beyond just being, mind-blowing, why does this actually matter for us day to day?
Oh, it's crucial. Your phone's GPS. It wouldn't work without corrections based on both special and general relativity.
Really? Because the satellites are moving fast and because of Earth's gravity.
Exactly right. We also needed to understand extreme things like black holes, neutron stars. Even the expansion of the whole universe relies on general relativity.
So it's not just theory, it's built into how we navigate and understand the cosmos.
Absolutely fundamental.
Okay, so summing up, time, space, gravity, they're not separate things. They're all part of this dynamic, stretchy cosmic dance.
A big, interconnected cosmic adventure, as the source puts it.
Right, so here's something maybe to chew on. What does it really mean for time itself to be flexible? Not some universal clock ticking the same everywhere, but something that stretches and squeezes depending on where you are and how fast you're going.
Yeah, what does that imply about, well, everything. Definitely something to think about next time you look up at the stars.